Perv nerd. Remember?
Today's Wednesday.
It is indeed, my dear. Wednesday all day. All right, so we got done talking about intermolecular forces. Intermolecular forces are what determines if something is a solid, liquid, or gas. Then we went on, we talked about solids, liquids, and gases. If we heat things up, those intermolecular forces kind of fall apart and eventually go away when we get into gases. And that's what's going to lead us to gases. So today we're going to talk about something called the ideal gas law. Now, there are other gas laws. We taught you other gas laws back in regular chem. Those gas laws those formulas do not appear on the AP formula sheet. Okay, but sometimes they're handy to work with. So if you are so inclined to, that guy can get you out of a few situations. The one thing that this doesn't take into account, that this does, is the ideal gas law takes into account the amount of gas that's in the container. And that's what the N is for. And we'll talk about that in a couple minutes. Okay. But this is the combined gas law. If you have pressure, volume, and your temperature is held steady, then you can get rid of that bottom line, and that's Boyle's law. Okay. If you have volume that's held steady, then you get rid of the V, and that's pressure over temperature, pressure, temperature. That is Gay-Lussac's law. Okay. And then if you have volume and temperature, that would be Charles's law. Okay. So this will get you out of a few situations occasionally, just having that one kind of in your toolbox. Can you get around it? Yeah. But sometimes it's just nice to have a few of those things. All right. So this is what I was talking about in terms of Boyle's law, Charles's law. We also have Avogadro's law that we didn't really do much with in honors or regular chem. But that one also exists where we look at the volume, and if we change and we add more gas in, how is that going to change our volume? So that's what Avogadro's law is. Okay. The ideal gas law is PV equals nRT. Your P is pressure, your V is liters, N is moles, R is a universal gas constant, and temperature has to be in Kelvin. They give you, Gabe, where are you at? There you go. Welcome back. They give you this on your formula sheet. They give you this on your formula sheet, and they give you this on your formula sheet. They'll also give you a couple other gas constants on your formula sheet. And the way you know which one you want to use is you look to see what unit your pressure is given in, or what unit you want to solve your pressure into. And this R value is what's going to do that for you. Okay. Make sure that you always check your units. Make sure that they're going to cancel out. If they don't cancel out, then maybe you didn't change your temperature to Kelvin and you forgot that part. Okay. If you look at your R value, though, it's going to tell you what all of these things need to be in. Okay. Your volume has to be in liters. Your pressure has to be in torr. Your mole value, your amount of gas has to be in moles. So if it's in grams, you got to get it into moles. How do you do that? What do you use to get from grams to moles? Atomic mass. Okay. Right? Because all of the atomic masses on the periodic table, their units are grams per mole. And then the K is Kelvin. Okay, you can rearrange this equation to solve for molar mass or to solve for density. if you're so inclined and your algebra does not fail you. Good luck, some of you. All right, here we go.
I like shapes.
Huh?
I like shapes.
You like shapes? Also on your formula sheet, there is Dalton's law of partial pressure, I believe is on there as well. Yep. Yeah. So Dalton's law of partial pressure is on there. It's the second one down on your formula sheet. And it just says that if you know the pressure of the two gases, if you add them together in a container and you add those pressures, then that's going to be the pressure of the overall system. Or if you have just an overall system like you're going to have in lab on Friday, okay, and you know the total and you know the pressure of one of these, you can solve for the pressure of the other just by subtracting. Does that make sense? Okay, so that's Dalton's law of partial pressure. This is essentially, we're not heating anything, but this is similar to what we're going to be doing for lab on, I'm going to move this thing and then it's going to jump me out of here. I need to get to some of that stuff. There we go. This is similar to what we're going to be doing in lab next week. Instead of having a Bunsen burner here and a test tube, you're going to have a flask. That flask is going to have water in it. And you're going to drop a piece of Alka-Seltzer down inside the flask and then cover it with a stopper. Okay. That's going to generate gases. And that's going to flow through this tube. This is water inside here. This container is completely filled with water. You're going to have a graduated cylinder here, okay? And you're going to snake this tubing up underneath here. When you drop that Alka-Seltzer into the Erlenmeyer flask, it's going to generate the gas and it's going to bubble up into here and it's going to displace some of the water. And however much water is displaced here is how much gas you generated from that reaction. Okay. Well, that didn't line up very well, did it? Well, there we go. That's better. All right. So this is water vapor pressure table. So you are going to find tomorrow or Friday when you do the lab, you're going to find what temperature the water in your tub is. And then that's going to give you the pressure from the water. Because there is a little bit of vapor pressure from the water that's experienced. Because some of that water will change into gas, right? And you have to subtract that away from the rest of the gas that's inside there to figure out your pressure. Mole fraction is also part of this, where you need to know how to do a mole fraction. So a fraction is just a part over whole, right? If I say that half of you are sophomores in here or juniors or whatever, okay, then 1 out of every 2 of you, because 2 would be the whole, 1 would be the part, okay? It's a mole fraction. This is just part over the whole. So mole fraction, a lot of times they'll do this fancy EA stuff here. I don't usually do the EA stuff, okay? What I like to do is I like to do X and then whatever material it is, because that's easier for me to keep track of in my head than have to go back and go, Okay, A was O2 and B was, you know what I mean? It's less conversion in my head. And there's a lot going on up here, so I try to narrow it down a little bit, y'all. All right. And then we had H2. Okay. So mixture is 3 moles of oxygen and 4 moles of H2. We need to figure out the mole fraction of O2 and the mole fraction of H2. So the mole fraction of O2 would be 3 over what? 7, because it would be the total, right? And 3 and 4 is 7. So over 7. And then you just multiply that out or divide that out, and it looks like it's 0.43. Okay. And then the H2 would be 4.0 over 7.0. So that would end up being what? Subtract this from 1. Can you do that in your head? 57.57. Yep. Mole fractions are always going to be a decimal number because it's always a part of a whole. If you've got a part of that whole, it's always going to end up being a decimal. It's almost like doing a percent without going to the end and multiplying by 100. It's essentially the same thing. That make sense? All right. We have a little kind of reaction is this? Let's go back to last year. Decomposition, right? We're decomposing something. Okay. Giving off some calcium oxide and carbon dioxide. Okay, so if we are using our PV equals nRT formula for this, what am I solving for there? Which variable? N. Okay, good. So I want to isolate and get N by itself. How do we do that?
By RT.
Yep. So N is going to equal PV over RT. Did I lose anybody with my algebra? Good with that? All right. Now we start going up and substituting things in. My pressure is given as 1.00 atm. My volume is what?
35 liters.
35 liters. Okay. Now I got to figure out my R value. So I'm going to go back to my formula sheet. Okay. And I'm going to look for an R value that has what unit in it? ATM. Okay. When I do that, I find 0.08206. Oh, I wish I could change my ink color. This is going to be liters ATM. And then they've got mole -1 K raised to the -1. What does that mean? So this is what they have written down on there. What do these -1s mean? Would you like to buy a vowel? Inverse, yes. What does inverse mean? Opposite side. So if these have -1s on them and these reside on the bottom, where are these units going to go? On the top. So this mole is going to go up here and Kelvin is going to go up there. Now, I still need to put one more thing down before I can start to crunch in my calculator. Temperature. But what's the problem with my temperature? It's in Celsius. I've got to get that sucker into Kelvin, so I need to add 273. Okay, so when I add 273, that comes out to 710 Kelvin. All right, now I can start getting rid of and canceling a whole bunch of units. Okay, my ATM will cancel out. My liters will cancel, if I can find them. And my Kelvin will cancel. And that's going to leave me with what unit? And that's what N is calculated in moles. So by canceling out all those units, I've kind of verified to myself that I'm solving for the right item. Okay? So when I do that, I end up with how many moles? I guess I don't have that calculated out. Ugh. Ugh. I get my new HDMI cable. I ordered a 20-footer. So hopefully that will take care of this, having to jump over everything. All right, 35. I'm going to hit divide. Before I hit another key, what's the next key that I need to hit after divide? Parentheses, okay? So 0.08206 times 710 in my parentheses, it equals. All right, I have my, why are you, oh God, really? Why are you doing this to me? Why? Why? There we go. So N is going to equal 0.60, how many sig figs? 2 sig figs. Okay, you see how I got 2 sig figs? I looked at all of the things that I'm multiplying and dividing. What's my fewest number of sig figs? 2 in 35. So my answer has to be 2 sig figs. So this is going to be 600, so that's right. I've got 2 sig figs down. Zeros at the beginning of a number are never significant. Zeros at the end of a number where there's a decimal are. So I have 2 sig figs written down here right now. And this is going to be moles of what? Huh? Just be patient with me.
CO3, calcium.
No, this is a solid. I don't have gas pressure from a solid. CO2. Ah, yes. This is moles of CO2. But they didn't want to know moles of CO2. If you go back, though, to your old friend, stoichiometry, then you will notice that if I have 0.6 moles of this, how much of this did I have to start with? 0.6 moles. They're in a 1-to-1 ratio. So that means for every 0.6 moles of this generated, I had to start with 0.6 moles of this guy. That makes sense? So now I've got 0.60 moles of CaCO3. And what can I do to get that into grams?
Divide by the atomic mass. Multiply.
Now let's multiply, okay? Because the atomic mass is going to be, is it 100.1? 100.1 grams for every 1 mole. If you use your dimensional analysis, it'll prevent you from dividing when you should be multiplying because you want to cancel out those moles. Did I lose anybody with this 100.1? Everybody know where I got 100.1 from? Yep, periodic table. So I added a calcium, a carbon, and 3 oxygens together. Okay. All I have to do is multiply through then, and that means that I started with 60. How many sig figs are in my answer right now? 1. I need 2. So what do I need to do? Just point. If I do 0.0, now I've got how many sig figs? 3. I only want 2. And that's going to be grams of CaCO3, and that is your answer. All righty. We do. I do, you do, we do. All right, you ready? Ready? All right. We've got basketball here. It was sadly left out in winter. The temperature got a little chilly. A little frost on the pumpkins there. Has a volume of 6.88 liters. Pressure is 0.795. How many moles of gas are in the basketball? And what is the partial pressure of oxygen in that basketball? What am I solving for? Moles. So N equals PV over RT. My pressure then, it says, is 0.795. I might have my units wrong on my answer key. I should have my units on here though. So that is going to be ATM. I have my volume in liters. That is 6.88 liters. I'm going to select my R value based on my pressure. And that is ATM.
At this time, if you're a ninth grader and you want your picture retaken, you can head to the small auditorium at this time. Only ninth graders, if you need your picture retaken and do not receive a blue slip, you should head to the small auditorium at this time. Again, only ninth grade.
Okay. And then I need to get my pressure, my temperature in Kelvin. So that's going to be what? Be able to do that in your head. 271 Kelvin. All right. I'm going to make sure that my units are going to cancel out here and leave me with moles. So I probably have this set up right at this point. And I got 0.795. I got 6.88. Parentheses 0.08206. 271 in parentheses. How many sig figs in my answer? 3. My calculator kicked back to me 0.2459, but that's going to round this guy up to a 6, and that's going to be moles. Now, they wanted to know at the mole fraction of oxygen. is that. So if I have oxygen, how many moles, what is the partial pressure of oxygen in the basketball? So the mole fraction would be 0.209. That's going to be by moles. And I'm trying to figure out pressure here. So pressure is going to equal nRT over V. Okay? Pressure equals nRT over V. Everybody good with that?
Yeah.
Okay. Now I'm going to sub in my moles here. You can pick what unit, because they didn't specify what unit they wanted you to be in for the oxygen. Okay. So you can pick whatever unit you want. I'm going to stick with ATM because I've got that one memorized at this point. So I'm going to go 0.08206. That is ATM liters over mole Kelvin. Okay, that's my units for my R. And then my temperature we determined was 271 Kelvin. I still need to get my volume in the bottom, which we said was, where's my volume? 6.88 liters. And you asked me, but Lippy, how do I know that the oxygen is that volume when that's the entire gas? Because the oxygen, just like every other gas in there, is going to spread as far and wide as it possibly can. Okay, so if that container is 6.88, that's the volume of your oxygen, because there are virtually no intermolecular forces present to hold that together tighter. All right, so my Kelvin's canceling, my moles are canceling, my liters are canceling, and that's going to leave me with what unit? ATM. Is that a unit of pressure?
Yes.
Is that what we're trying to solve for?
Yes. Yep.
All right, I ended up with my pressure equaling 0.676 ATM and I think I calculated that right. Okay. All right, here we go then. That's the pressure of O2. What did I do wrong, Maddie?
Not wrong, but why did we calculate the first one?
Why do we do this thing?
Yeah.
Because they asked how many moles of gas were in it.
So that's the moles of all of them?
That's the moles of gas. Yep.
And then the we calculated.
And then this is this guy right here. And this guy right here. Okay. Guess what you have for homework tonight? 3.4. Good job.
Yeah.
Yep. Okay, watch the video.